Hello, everyone. We're going to give a demo about our bias detection and correction tools. But before we go to our GitHub repo, let's talk about the data set that we basically utilized. It's a medical data set that has a collection of individuals where each row is an individual who had or did not have a brain stroke in the past. We have a mix of input features. The first one is race and ethnicity, which is our demographic or the sensitive feature. We have age, we have some medical features such as hypertension, heart disease, average glucose level, BMI, and we have marital status as well as some social features such as work type and residence type. And we're going to use this data set to demonstrate our tool. Now, after we go to our GitHub repo, we clone the repo, then we open VS Code, create a new environment, and run this command, which is pip install requirements.txt, to install all of the packages that we need in order to run these Python scripts. On the left-hand side, we can see we have inputs, outputs, and the two Python scripts that we're going to use. We're going to start with measure disparity.py, which a Python script that has only a single function that takes a data frame that holds the model's predictions, the file name, then the name of the column that has the true labels, the name of the column that has the model's original predictions, and the sensitive feature or the name of the sensitive feature. And in this case, we have race or ethnicity. The goal of this script is to measure the social bias in the original model's prediction. So we run the script or the single function, and the output that we're going to get is basically two parts. The first one is a small CSV file that shows the scores by subgroup. We can see here we have Hispanics and whites, and we have several fairness metrics as well as performance metrics, but it's better to view this in the graph. So if we click on the PD biasing predictions fairness graph, we can see on the top, we have the first fairness metric, which is demographic parity. Then the second one, true positive rate, which is basically the equal opportunity metric. Then we have the false positive rate. The true positive rate and the false positive rate taken together, they constitute the equalized odds metric. So we suggest in a healthcare setting to focus on improving the equalized odds metric. In other words, we want the true positive rate between the two subclasses to be almost equal, and we want the false positive rate between these two classes to be also almost equal, or at least improved to a certain extent. Towards the bottom, we can see different performance metrics such as accuracy, balanced accuracy, F1 score, and AUC, because we have to keep in mind that there is a trade-off between performance metrics and fairness metrics. So we want to hit the sweet spot of mitigating bias without sacrificing much of the performance of our model. And this takes us to the mitigate disparity.py script. This script basically takes a training and a testing data frames, and these are from the original data set that we talked about brain strokes. It takes the name of the sensitive feature, the name of the target variable, and we have the base scikit-learn model. And what we mean by that is any model supported or like included in the scikit-learn library that we could use as the original model to make our predictions. Then with that, we have the parameters of that base model that we're going to use when we perform grid search CV. Then we have CV, which correspond to cross-validation, the number of folds. Then at the end, we have the fairness metric constraint or the fairness metric. And in our case, as we said, we suggest using equalized odds, although we can use demographic parity or equal opportunity. Then we just run this single function or this script, and it's going to generate two kinds of outputs. The first one is under the outputs folder, which is the debiasing model.sav. This is the debiasing model that we're going to use for future predictions. And the second output that we have is the post debiasing predictions under the inputs folder. If we click on that, it's basically the same data frame that we used in the beginning when we measured disparity in the original model. So we wanted to create a data frame that holds the predictions the debiasing model made, and we have the race or ethnicity, which is our sensitive feature, and we have our true label, which is the ground truth of the data set. Then we go back to the measure disparity.py, and we see if there is any improvement in the fairness metrics. So we changed the name or the path where the data frame is, because now we have the post debiasing one. Then we again run the Python script, and what we get is the same, a graph and a CSV file under outputs called post debiasing. If we clicked on the graph, we can see, if we clicked on the graph, that on the top we have the demographic parity. This is the pre one. We're going to compare both of them. We have on the left side, we have the pre-debiasing, and on the right-hand side, we have the post-debiasing graphs. We can see on the top, demographic parity has improved slightly, although this was not our focus. The second graph, we can see there is a huge improvement. Now the true positive rate or the equal opportunity is almost the same. The third graph, we can see how the false positive rate for the Hispanic subgroup has increased drastically, although it's still not equal to the false positive rate of the white subgroup, but there is certainly improvement. And we can see that there isn't much sacrifice in the performance metrics as well. So we could say that we successfully debiased we debiased the health disparity in the data set. And thank you so much.